Okay, so first, number 2. We want to draw a free body diagram of the beam. And it's going over a pulley. And the mass is 350. So first, that weight force is going to be 350 times 9.81. So 33.5. Okay. Well, first you have to understand what I'm drawing here. This, I guess I made this problem before I got a bit better at using these drawing tools, but that's supposed to be a pin joint down there, a hinge joint down at the bottom. So if you didn't interpret that right, then that's not your fault. That's just, but, okay, so here's the closed outline. And then the weight acts at the middle. And that is 33.5. And now we have to go and look at all the places that the surroundings make contact. I'll start down at the pin joint. The rule for a pin joint is it restricts both components of translation, but no rotation. So that's an unknown force vector. So I'll call that R. And then the
rotation, because it's like still rotated a little bit, like the hinge joint itself can like allow
the hinge allows rotation. So remember that the forces have to do with the motions that aren't there, not the motions that are there.
Yeah, because I'm thinking about it as a matter of motion, not about like force.
Exactly. So yeah, think about the degrees of freedom that are disallowed by the joint. Okay, so it doesn't disallow rotation, so there's no couple. Now we'll go to that roller. The rule for a roller is that's perpendicular to the surface toward the body. So that's going to be I think so. Let's look.
Are we assuming no height because it's not specified?
On a free body diagram, it doesn't matter since we're not doing any calculations, but you're right that if it's ever not specified on something that looks slender, you can just assume that the thickness is 0 or whatever.
I don't think you specifically said the roller did that.
I guess not.
But you did an example with one later on.
Okay, so a roller works the same as a frictionless contact. Okay, so then this is going to be perpendicular to the surface toward the body. I have to give that a name that's not R, so I'll call that N. And now the only two places that are left are the forces applied by that cable. The pulley doesn't touch this body, so we don't have to treat the pulley explicitly, you know. So all we have is a cable force here that's parallel to the cable away from the body. And then another one here that's parallel to the cable away from the body. It's the same cable just going over a pulley, so it's the same T. Yes?
How do we know the cable is pulling and not pushing?
Cables can only pull. Yep.
What is R in here?
Reaction. Oh, so that is the force vector, the unknown force vector that keeps that bottom point of that beam from translating anywhere. Okay? So if you gave this thing a little nudge and this joint wasn't here, that end would move. The joint keeps it from moving. Yep.
Professor, so for like the joint, when can we say what specific angle it is, and when do we need to do the R general one?
Yeah, you can only say the specific angle when it is a frictionless contact or a roller.
Okay.
Or a pin and slot.
P has the same magnitude, right? Well, or would be the P anyway.
The X and Y components?
Yeah.
Or T, did you say?
P.
T, yes. It's the same in both. That's why we gave it the same variable name. So if we solve for T once, we've solved for it. Yeah. Any other questions? All right, so let's go to number 3. Okay, so this it's this curved body, and it's connected to a cable in 2 places that goes over a pulley. It's connected to a roller, and then there's a fixed joint at the top. One thing I want to point out is this one. Well, no, I don't think this one shouldn't be solvable either, because we have 1, 2, 3, 4 variables. So Newton's laws only gives us 3 equations for a rigid body. So we can do this free body diagram, and all those forces are right, but we don't have a way to solve for those. And we won't in number 3 either. Yep.
We have 3 variables, R, N, and T.
R is a vector, so that's an X and a Y component. Okay, so the free body diagram for this one. Lovely. And then, okay, so there's a weight. The body's mass is 1,050 kilograms. That's very specific and very heavy.
Where would technically the center of mass be somewhere above?
Yes, actually, you're right about that. So yes, the center of mass would be somewhere here. And later we'll be able to calculate where that is. Yep. And now we'll go to the contact forces. Up at the ceiling, that's a fixed joint. A fixed joint provides an unknown force vector and a couple. So I'll put this in as unknown force vector that I'll call, let's say, R1. That's an X and a Y component. And then we also have a couple here. I'll call that M1.
And which one has priority there, or are they the same?
Neither one has priority, but they're different things when you put them into the equations. That R1 is a force, so you'd have to figure out the row vector for that and put those components in the column for forces. Bless you. The M1 is a couple, and so you wouldn't have a force, you wouldn't have a row vector, you just put that in the moment column. Now the roller here, the rule is that is perpendicular to the surface toward the chosen body. That's kind of perpendicular, I don't know. Perpendicular to the tangent. I'll call that R2.
Is that also a vector? No, we know the direction.
Right, we know the direction. I mean, they're all vectors, but that variable is not a vector variable, right? And then we'll go to the cable forces. And again, that pulley isn't touching this body, so all we care about are those two cable contacts. So we have one going this way, I'll call that T, and then one going this way, and I'll call that T. Okay, so it's really just about, so you put the weight force in, and then you go through, identify where there's contact, and at each of those contacts, you just follow the rules, you know?
Do we need to memorize like the list of rules?
Yeah, I'm not going to give you a list of pictures or anything like that, right? So, but remember that you can always, like, maybe better than memorizing it is just getting used to thinking like, what degrees of freedom does this eliminate? You know. So is this one solvable for these loads? We have two variables for R1, the X and Y components, a third for M1, a fourth, and a fifth. So we have 5 variables. Newton's laws only give us 3 equations. So we're out of luck here unless we're given more information. Yep.
What degrees of motion does a frictionless contact limit?
So if you think first about trying to move perpendicularly to this, it limits a motion perpendicular to that contact, perpendicular to that surface, you know. Then, so once you've chosen that as your first one, so you have a force component that's perpendicular to that contact, but it could move side to side, like 90 degrees from that, so you don't have any second component.
And it could rotate around as the joint as a
Yeah, exactly. If all that other stuff was gone, this could rotate about that point. Yes.
And is that when you say N? Like
Yeah.
normal force?
Right.
And
Yes.
For the force down, that's the M times G, right?
Right.
So it's like the middle of the circle.
Oh, I didn't do that, did I?
Semicircle. Is it supposed to, could it just be on the bottom, or does that have
Well,
to be placed in the middle?
It acts from the center of mass, and the center of mass of this shape is up in the blank part. So really, you should put it up there. We haven't talked about that yet. We'll get to calculations of centers of mass for more complicated shapes like this. This weight, by the way, I didn't write it in. It's 10,300.5. Why do we have it? Because that's a fixed joint, and a fixed joint limits any translation. That's what the force vector is, and it also doesn't allow a rotation, so that's why the couple is there. Yes?
If we had like 2 fixed joints, like
Mhm.
does that appear in statics?
Well,
Like if the left end was also connected?
so we wouldn't be able to, so you could do the free body diagram and it would appear just, with 3 more variables. You couldn't use statics to calculate what those loads are, because for a single body, you only have 3 equations, and then you'd have at a minimum 6 variables. You can still do that calculation, but it involves stuff that we learn in deform in mechanics of materials. And it's called a statically indeterminate system. Both of these so far have been statically indeterminate systems. You don't have enough statics equations to solve it, but you can do other stuff to solve it. Harder stuff. Any other questions on these? Okay, and then the last one is 5. Okay, and there's kind of 2 different ways you could think of 5. If you're trying to solve this, the easiest way to think of 5 would be this. So I'm going to draw a red line around what I'm isolating. Okay, so I'm going to take all this, and then I'm going to include that cable in what I'm isolating. Okay. So if you do this, I'm going to do this free body diagram 2 ways. So this is the smart way. This is the way where you can sort of get at some calculations. So this free body diagram looks like, the free body looks like there's this thing. Okay, so that's my free body. And now we can think about the loads. There's a weight force. This, we don't know what the mass is, I guess. I'll just call that mg. Yeah.
Does including the pulley change the center of mass?
Well, if the pulley had a significant mass compared to the body, I guess in this class, I can't think of a time where I consider the pulley to have significant mass. So you can just always treat it like 0. Also, you'll see in dynamics that if the wheel of the pulley has a mass, it actually changes the behavior of bodies when they're accelerating. So
When I drew mine, I just drew a beam and then
yeah, I'll do it that way too. Okay, but I want to show how these 2 ways of thinking about it are different, and why sometimes it's useful to think a little bit about what you're going to isolate, what you're going to include in your body. Okay. So okay, now over here we have a pin or a hinge joint. I'll call that R. I'll call that R2, working from left to right. I'm going to call the one on the left R1. And then over at the pin and slot joint, that is a force that's perpendicular to the slot. That's just a scalar R1, I'll call it.
how do we know the direction? Could it be going on top?
Down?
Yeah, down.
Yes, it could be going down. So with pin and slot joints, whichever way, I could have drawn it down or drawn it up, and it can come out positive or negative. Okay? If I did the calculations with it going up and you did it with the calculations going down, we would get the same absolute value of answer and we would get opposite signs. And now the last one is where's the final third place where the surroundings contact the boundary? It's where the cable that I didn't include contacts the cable I did include. So that's a pulling force this way. And that's, I'll call it T.
But if I were to put, I drew the pulley by itself and then had T coming this way and then T coming out of the pulley like this. Is that practically the same thing?
Okay, so let's do that one too. So let's think of how many variables we have here. I'm assuming that we knew mg, that mass just wasn't given. So we have 1, 2, 3, 4 variables. And let's think about some of the other possibilities. So so now let's say we go like this. Okay, so we have mg down again. We have R2 and R1. And we have T this way, T this way. And then that cable is touching one more point. It's touching here. So we have T that way. And that's a fine way to do it. When you do your calculations, you'll see that this T and T don't end up having any effect. They cancel each other out as forces. They cancel each other out as couples. So it basically reduces to what we have here above.
What? So you have to draw the pulley here because it is like actually on the beam.
Okay, so let's do it now without the pulley and see.
Can you do that?
You can, but I'm going to show you why in this case this works better. Okay, it's not wrong for a free body diagram. You can totally do it that way. But when you went to the calculations, you'd be in trouble here. Well, this is 4 variables, so you're in trouble no matter what, unless you are given one of these values. But let's see what happens if we don't include the pulley. So we have mg. Here we have what I called R2, and here we have R1. There's a contact with the beam at the left end where the cable touches it, so we have a T there. And then we also have a fixed joint between the base, or whatever you call it, of the pulley and the body. So here, now I would have to put in an unknown force vector R3, let's call it, and an unknown couple M3. And so in this case, that's a perfectly fine free body diagram, but when you go to do equations, it's not as useful as the other ones because you have 1, 2, 3, 4, 5, 6, 7 variables. Yep.
Sorry, trying to
Mm-hmm.
put my question into words. It seems like which one you do depends on what you're trying to find out.
Mm-hmm.
Like if you're trying to find out the force, how many screws you need to attach the pulley to the
Right.
pull with, then you need to do the last one.
Right.
But the first one is okay. I put like 7 million.
Yeah.
screws in there. That's not coming out.
Right. So yes, you're right. I think what you would want to do is you'd want to use the simplest one you can to find some variables, and then you'd kind of want to piggyback on that. So like, for example, now that we know, if we could calculate what that T is based on a simpler one, now you could just isolate the pulley system. It has a fixed joint at the bottom, but put that in, but now you know what those T's are, and you could sort of piggyback. Okay. But yes, that is very true, and that is kind of the principle of internal loads that we'll get to in deform in the spring if you take that. Being very conscious of where you want to make your cuts so you can calculate, what loads are happening where at a specific place.
So overall, the last one is okay, but just for the body diagram.
R-
But when
yeah.
you wanna use it, then it's like trouble.
Right. Yeah, all I'm trying to do with these problems is get you used to the idea of identifying joint types and putting in the loads associated with those joint types. So for those purposes, this is perfectly fine. But once you start trying to do calculations, ideally what would happen is, okay, like why would you see that right away? Like, maybe you wouldn't. I don't remember, when I first did this problem, what I saw and what I didn't see. But if you look at this and you just say like 7 variables, you can't think of any other ways to do it, then you think like, is there any way I could simplify this problem? Calculate other stuff. And yes, if you include some other stuff inside your system, then, it's easier to calculate some things. Yep. Okay. So now we're going to start going through 3D joints.
Is 3D joints different than rigid?
Well, it's still rigid bodies, but it's 3D rigid bodies. So let's call it rigid bodies, 3D joints. Okay, so remember that when we talked about 2D joints, in 2D, a rigid body has 3 degrees of freedom. Uh, 2 translational and 1 rotational. In 3D, a rigid body has 6 degrees of freedom. And that is 3 translational and 3 rotational. So if I draw like a 3D rectangular solid, it can translate along this axis, or this axis. Whoop. And it can rotate about each one of those axes, this way, or this way. You couldn't rotate about the X and Y axes and still be a motion in the XY plane, because the body would be, if you try to rotate about X or about Y, the body is rotating out of the plane. But now that you're in 3D, you can rotate about any of these axes and it's still 3-dimensional motion. Okay. So you would expect, the way the joints worked in 2D was we had all these different joint categories based on how many degrees of freedom were eliminated. We would expect to start out with 1 and go all the way up to 6 this time. With 2D, we started at 1 and went up to 3. And that's what we're going to do. Okay, so we're going to start with things that only restrict 1 degree of freedom, and then we're going to go all the way up to a fixed joint or a weld joint in 3 dimensions, introduces 6 variables and restricts 6 degrees of freedom. Okay, so joint category 1. So this, or all of these, apply a force in a known direction They eliminate 1 degree of translational freedom. And they introduce 1 variable into Newton's laws. And so the first is frictionless contact. Um, so if this is body 1 that's making frictionless contact with, this is supposed to be like a surface in 3 dimensions, a free body diagram. If this is the angle of the contact, it's going to be perpendicular to that surface of contact toward the chosen body. So that's just like it was before. It just has to be perpendicular to a surface instead of a line now. The second one is a roller. And it's important here that this type of roller is a ball, not a wheel. And the reason for that is a wheel has a preferred direction. So it actually, if there's any friction on a wheel, it actually does limit translation perpendicular to the rolling path, And so this looks like maybe these 3D drawings get a little hairy, but so a roller there. And a free body diagram. Again, if the surface is this way, the force is perpendicular to the surface.
Could be a ball and socket joint. Could be a ball roller.
No, a ball and socket joint is going to be something else, because you can imagine something connected to a ball and socket joint. That point is locked in place, so it limits the translation of that point.
But it is a ball in a socket so that it can't go anywhere, but it can roll free.
Yeah, this can roll. This is like the rollers on these are wheels, but office chairs that have balls on the bottom, it's like that. One thing to notice about these, in both of these 2 cases, R must be positive. Any other questions about those 2?
Right, that's for both frictionless contact and roller.
Yes.
So
Right.
R has to be towards the body.
All R has to be towards the body. If R was away from the body, it would be like it's hanging onto the floor somehow, like glue or something, and that can't happen.
Or it would just,
If they separate, then there's no force at all. So it really would be like it hanging on somehow, you know. And now we'll go to joint category 2. These are, so there's only one of these, and it applies force components in 2 directions. So how many degrees of freedom does it eliminate? Yep. And that's translational degrees of freedom. And then how many variables does it introduce into Newton's laws? Yep. So the one in this category is a wheel with a preferred direction.
does that mean it only spins in one direction? Or
No, it
prefers-
means that it has a path direction. You know, like think of a like the wheel. Think of a unicycle. That's one wheel. You know, so friction keeps that wheel from sliding along the concrete side to side. So that's, but it allows it to roll forward and back. So that's what I mean by preferred direction. It can move forward and back. It doesn't eliminate that degree of freedom, but it does eliminate side to side translation. Okay. So now I'm going to spend the rest of the class trying to draw this. And its preferred direction. Oh my God, that went haywire. Okay, its preferred direction is this. And a free body diagram looks like this. So if there's the wheel, and let's say that the path is this. Let's call that the like permitted path. That's the direction it rolls. There's a force perpendicular to that this way.
And that force has to be towards the body.
That's right. And I'll call that N. That's the one that we're used to. But now there's also a force like this.
Z direction.
Right. I'll call that F. And that has to be perpendicular to this path also.
So could you also think of it as like a wheel in a slot? can't move side, it limits, and at least in this picture, and I'm guessing in most.
Yeah. Mhm.
Limits your movement in the Z direction.
Yeah.
It can't go.
Yeah, you're
go
thinking
up
about
and
that
down.
right. Yep.
You can go side to side, but not.
Any other questions about that one? Where are we at? 10 more minutes. So let's do one more. This is an important one, and then we'll finish next time. So next is joint category 3. This is a force vector with an unknown direction. It eliminates 3 translational degrees of freedom. And it introduces 3 variables. Into Newton's laws. And that is a ball and socket joint. So that's a joint like this, that those 2 pieces can rotate in any direction relative to each other. So the other ones have kind of been things that we tend to use with one of the things being a body that we might isolate and one being the ground. This one, I'm going to think of a body 1 and a body 2, and I'm going to draw both of these 2 free body diagrams. So a free body diagram for body 1. This is an unknown force vector with 3 components. So I'm going to draw little vectors in each of the 3 axis directions. I'll call this the force on 1 by 2. And then a free body diagram of body 2. Again, I'm going to draw 1, 2, 3 vectors in the coordinate system axis directions. This is the force on 2 by 1, and that's the same thing as negative force on 1 by 2. Any questions about that? Okay, so I'm going to stop there because the next 2 get a little more complicated.
I have one.
Yeah.
Talk about joints that eliminate like a pin and a pin joint, but it can only move 90 degrees.
No, and the reason that we're not is because we're talking about statics. And so if the thing isn't moving, it's either at that limit or it's not at that limit. If it's at the limit, it's a different kind of joint. You know what I mean? It restricts that motion. In a way, that's the same reason that we talk about friction the way we do. Either friction is engaged, in which case we treat it like it eliminates all motion, or it's not engaged and we treat it like it's not there.
Are you going to do the exams on Friday?
No, I'm not. Sorry. I wish I could give you a different answer, but I have a